Good morning, here yet again for another lovely session of CENG 3325 Structural Analysis. This will be the 29th lecture in the video series, and today we're going to be discussing approximate methods for solving statically indeterminate structures. So let's consider this, approximate methods for indeterminate structures. For indeterminate structures. So, what do we mean when we say approximate methods? Well, first of all, we should look at determinate versus indeterminate. For indeterminate, or for determinate, we of course mean that they can be solved using the laws of statics alone. All member forces can be solved for using statics. All member forces can be found using statics alone. By statics alone. And with indeterminate, of course, that is not possible. Instead, it's almost like the number of unknowns is greater than the number of equations of equilibrium, or greater than the number of equations. Unknowns greater than the number of equations of equilibrium, or just equations available. So what we need to do is we need to find another equation or more equations that we can use to simplify the process, or if not simplify the process, just get to produce some other relationship that we can add to find unknown forces. And so what have we looked at so far? So far we've considered a few things. We've considered things like compatibility, compatible deformations. We have considered things like virtual work and the force method. And really, all of these rely on both the area of the members, the modulus elasticity of the members, the moment of inertia of the members, these sort of things. So they all rely on the stiffness of the members, dependent on member stiffness, on exact member stiffness. And these are fairly accurate methods. So the stiffness methods like this, these methods are very versatile. Let's see, for finding precise values of forces, for solving even complex shapes and complex frames, even very complex frames. But what's their downside? What's the downside of these methods?
Very long.
They're very long, exactly. So we have seen examples already where to find the displacement on one joint, it might take you, an hour to solve for and multiple levels of integration to solve for the deflection on a single joint. So the downside is that they are quite lengthy in time. The downside is they are time consuming, as we have already seen. Which can be fine, especially if you're building them into computer method. If a computer is doing the calculations well, a computer can do the calculations that would take us, hours. They can do that in a fraction of a second. So, for computers, those types of methods are fine. That's what those types of methods, whether force or virtual work or elasticity, all of those things, those methods are built into a lot of computer software. However, oftentimes, especially when you're dealing with design, it can be useful to have a starting point. And so here's the question I want to ask you. In terms of design, so everything we've been doing so far has mainly been analysis. What about design? What if we were dealing with design? So for your analysis, it's fairly simple because you already have a design in mind. You already have a design in mind. And you can run through elastic methods fairly simply. Through any method depending on members very simply. Well, if not simply, but fairly straightforward. Any problems or analyses involving member stiffness fairly easily. Just by plugging and chugging. But what about design? What is the difference between analysis and design, of course? Difference between analysis and design.
Design is from scratch.
Exactly, yes. Design, of course, you're starting from scratch. With design, you're going to be starting from scratch. So here's the question. If your methods are relying on your member stiffness to solve for your displacements, how do you even begin? So think about this. Consider something like the force method. If you are analyzing, or if you're doing design with the force method, you really have to start with the design, and then you'll input your loads and stiffness, and then in turn you'll get the performance, which would be both the stress and the strains and the displacements. Your performance, and then you'll have to take this and re-alter your design in order to refine it. Maybe make members thicker if need be, or stronger if need be, make them lighter if you can get away with that. Design is an iterative process. The problem is, though, because it's an iterative process, you need somewhere to start. So if you are relying on your, okay, maybe I should say based on displacements and stresses, you can alter your design. So again, though, if your method, for example, your force method is relying on the stiffness again is a function of your cross-sectional area, your moment of inertia, and your modulus elasticity. So how can you possibly get this loop started? If you're having to start from scratch and your method relies on already having design in hand, how can you possibly get that started? Any idea? How can you get that loop started? That's the problem. So everything we've looked at so far on all of these force methods and virtual work, etc., you have been given an initial design and said, here, run with this, see if this works. But what if I just say design something? How do you even begin that process? Tricky, huh?
You have a problem you need to solve, right?
Huh?
You have a problem you need to solve.
Yes, you definitely have a problem you need to solve.
You know the loads, you know what it's going to take, I guess.
Yes, so
you can cycle through different moment of inertias.
Yes.
Beams.
You could cycle through moment of inertias and things like that and just sort of guess, check, and revise, but there is actually a much better method. And this is where approximate methods really shine. So instead of just, picking random sections of the steel manual and seeing how they work, these are a way to design a structure or to come up with an initial design for a structure before you really begin lots of your loops of analysis. A good way for many structures to get your initial design. Your initial design. And so there are many different approximate methods, and all of them are just basically rules of thumb. And the way they work, all of them have the same basic process. They work via this. They basically say, okay, let us make an assumption about how load distributes through a structure. About how loads distribute through a structure. Or distribute through a frame. And based upon this, or this assumption effectively gives us another equation to solve for. Or this equation, this assumption will give us additional equations. Will produce additional relationships and therefore equations. Additional equations / relationships. / relationships. Okay. So again, just like with the force method, it's basically a way, or they are basically a way of taking an indeterminate structure and turning it into a determinate structure. And so then we take the via the assumptions of approximate assumptions, we'll take this indeterminate structure, put in some approximate assumptions, and on the other end, we'll have a determinate structure. Now, you would not want to rely on just these methods alone for designing a life-critical structure, but again, as a starting point for your analysis, it can be a very good method. Or if you want to find, for example, if you're doing a computer method, any computer program is going to first ask you to input sections. You can't, a computer structural analysis program is not going to be able to just, you can't just say, oh, I want a building that can withstand this many loads, or loads this large, or I want a building of this many stories and this footprint, and you press a button and poof, there's your design. That's not how structural analysis software works. You have to tell the program what kind of support conditions you want, what kind of geometries you want, what kind of member lengths, and then what kind of cross sections, and then it tells you, based on the loads that you tell it, what kind of deformations you'll have, what kind of stresses you'll have, that sort of thing. It is not a magic box. It is not a mystical genie. It cannot just poof and there's your building. Computers are great, but they're stupid and they don't really know much. So you need to give them a starting point, and that's really where one of the areas where Approximate Methods really shine. So again, now I suppose for certain very simple structures, you could use Approximate Methods for the entire design. So for example, if you're designing something like a I don't know, like a garden shed or something like that, something that you're not really, that's not really life critical, or for example, you could, let's look at when you could use approximate analyses alone. Designing by only approximate methods, without any further checks, when could you do this? By only approximate methods. You could use, for example, one very non-critical applications. Non-critical applications or structures. I always bring up a tool shed comes to mind. Hopefully there's no one living in your tool shed, otherwise that would be either scary or sad depending on the circumstances. Sad if you're living in the tool shed, scary if some unknown person is living in your tool shed. Anyway, so the idea of simple storage structures like that is, yes, you do want them to resist the wind and the rain and everything else, but there's nobody standing in them or sleeping in them or occupying the space most of the time. And you're probably not going to evacuate to the tool shed during the hurricane, at least I hope not. If the tool shed falls over during the hurricane, oh well. I guess some tools get wet, but I guess some tools might get ruined and some things might get ruined. But again, nobody is going to die if the tool shed falls over. Hopefully. Very non-critical structures such as a tool shed. Other things. Cases where you're content just massively overbuilding something. Where just utterly massively overbuilding something is possible. Is acceptable. Although, really, I feel hesitant to even mention this as a structural engineer because it's so anathema to everything we do. But the truth be told, in most cases, at least for small-scale wooden structures and things, if you really want, you can probably get away with just massively over-designing things. Although that does really, at that point, you're really not doing engineering anymore. You're just sort of doing approximate, looks good, seems strong enough type methods, just eyeballing it almost. So, I mean, you could do that. I mean, if you really wanted to, if you were incredibly lazy and just absolutely insisted on not doing any analysis and you didn't care about the cost and you didn't care about anything else, I mean, if I just wanted to build a structure and I did not care about the cost and my only one design objective was I didn't want to use any software and I didn't want to have to do any hard work, I could use Approximate Methods and just use a factor of safety of 5 or something absurd like that. I mean, I could do that. It's going to save myself some time as an engineer, but oh boy, am I going to have to pay it on the materials bill. But so that's usually not what we do, though. So Approximate Methods, I suppose if it was like, it's one of those desert island situations. If I have to do structural analysis while stranded on desert island, I suppose I might design structures using only Approximate Methods, but otherwise it may not be the ideal for pure design. So let's look at some examples of Approximate Methods. First of all, let's consider trusses. We're going to make a couple assumptions for trusses. Just like all of these approximate methods, they're going to be built on a couple assumptions. The first assumption And really, they're going to be two assumptions based off of the slenderness of the diagonals. So we will make an assumption based on the slenderness of the diagonals. The slenderness of the diagonals. Of the diagonal braces. So you have a truss, say a multi-panel truss, and we might have an indeterminate truss like this. So when I'm just drawing this as a line diagram, we don't really know anything yet about the slenderness of the braces. But let's discuss what kind of assumption we would want to make, or when we would make each. So when I say slenderness, consider this. There are different ways you can make these braces, depending on what they are. If we have an example of a slender brace, would be something like this. A slender brace would be something like a very light hollow tube section, maybe a hollow circular tube section, or a hollow square tube section, a very, very light one. Or most commonly, the one I see most common, would be a very light L angle, a very light angle. And when I say slender brace, basically what we're talking about is we're talking about something that will not be able to resist substantial compressive load. Able to resist substantial compressive load. Substantial compressive load. And so let's think about that. If I have something that is will not be able to resist substantial compressive load, that's not necessarily a problem, because as long as I have two of them, depending on how the loads on your structure are, this panel here, for example here, if this member here is in tension, then this one will typically be in compression. They tend to work as matched pairs. And so if one diagonal is in tension, the other will tend to be in compression. And so as long as I have two of these on the same panel, if each one is very slender, that's not necessarily a problem, because one can carry the other's load. However, if I had only a single diagonal, I couldn't get away with doing that usually, because again, if compression was demanded of that frame, of that bay here, or of that panel here, if I had a very slender member, it's just going to buckle. So slender members, if you go back to your Euler buckling, when we pull on a column, it doesn't undergo any kind of buckling. You can get the full strength out of a column, up to the full yield strength usually when you're in tension. But when you are in compression, you don't get that full strength. Instead, what happens is the column tends to buckle. So it will buckle like this. It will buckle something like this. Or if you brace it at the middle. So for example, if you brace it at the middle, like this, it will instead buckle in more of an S shape, like so. And also this will depend on your support conditions, whether you have a fixed column, whatever it might be. But again, the point being that when under elastic loading, columns tend to, or when under compression, columns will buckle rather than will tend to buckle at least, rather than be pulled apart under, or pushed apart under full axial stress, under full yield stress. So a slender brace is basically one that has, and so getting back to this, for Euler column buckling, the stouter the shape, a stout shape with a high moment of inertia, is what resists buckling. A high moment of inertia is what resists buckling.
So the column that's in tension, that's like pre-stressed, like formwork or something like that?
Okay, the question is, what would that column in tension be? Typically just a tension member.
Okay.
just a member carrying tension. You can think of it as pre-stressing if you want, but typically, to keep it simple, we can just say that's a tension member. So that is what a slender brace is, and then a non-slender brace is one that can resist buckling. A non-slender brace is one that can resist buckling. So this would be something like a W shape. If you make the diagonals of your truss out of something like a W shape, or other large rolled shape, especially like a C channel, that sort of thing, C channels, W shapes, good, strong, stout C channel, those sort of things, if those have enough moment of inertia, they have enough oomph that they are able to resist buckling. So, and based upon which of these we have, we are going to make a certain assumption about how loads distribute through the truss. Okay, so do you understand the difference between slender and non-slender braces here? That fairly clear? Okay, so assumptions. I'm going to list these as assumption 1 and assumption 2. We do not apply both of them. We pick one or the other. So there are 2 possible assumptions for trusses. Assumption 1. So again, we pick one or the other. We do not try to put both in the same truss. These are incompatible assumptions. So if we have long, slender braces, we assume that diagonals can carry no compressive force, can carry 0 compressive force, and that all panel shear is carried by, intention. And that all panel shear is carried in tension. That all panel shear is carried in tension. Okay. And then assumption 2, and I know we haven't discussed what panel shear is yet, but I will define that. If we have large rolled shapes or compact shapes, shapes for the braces that can resist buckling, we assume that each brace carries an equal magnitude load. We assume that each brace on a given panel carries equal load. With one in tension and one in compression. With one in tension and one in compression. With one in tension and one in compression. So, let's think about this here. With one in tension and one in compression. So, here, let me describe what I mean by panel shear. Let's discuss the concept of truss panel shear. Let's say we have a truss, something like this here. Let's say I have a truss like this. And Let's make it a fairly complex truss. Oh, something like this. Something like this here. Okay, so looking at this, how indeterminate is this? Well, let's look at our good old m plus r equals 2j. So how indeterminate is this? Well, number of members, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 members. And let's say this is also simply supported for simplicity's sake. So again, do we get that right? 8, and then 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, reactions would be 3. Plus 3, and the number of joints, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 2 times 10, 24 equals 20. Definitely not equal to 20. This truss is actually indeterminate to the 4th degree. Oh boy. Imagine trying to analyze that using the force method. Well, first of all, we don't have a redundant number of reactions, so that's going to be even more of a problem. So we're going to have to use internal redundancies and things like that. This is going to be an absolute mess. Oh boy. So I suppose we could use redundant reactions. We could make all of the reactions redundant, so all of the external reactions redundant, and then we'd still have to look up some other methods. I haven't taught you how to handle redundant internal forces, but there are methods of dealing with that. But still, at the end of the day, we would basically have redundant reactions or redundant forces A, B, C, and D, and we'd have deltas of all of those combinations. So we'd have like delta A, we'd have delta delta AA, delta BA, delta CA, delta DA, 16 different deltas. And we'd have to do virtual work method on each of those, every single one of those, in order to find this. We'd be here all day. And so this would be quite involved, to say the least. I'm content leaving the computer to do this one. However, what do I do to get my initial design to feed into the computer? Well, I can use approximate methods. And using just those assumptions, looking at this truss, I can see 4 easy equations that I can get to immediately make this a determinate system, or at least something that is determinate enough to get an initial design. So for example, let's say that there's a load on here, and let's say this load is, I don't know, let's apply a 30 kip load here, and, that's too boring. Let's say there's a 30 kip load here. 30 kip load here, and let's see, let's go ahead and we can get the reactions if we know well, I don't even know the dimensions here. Let's just say it's 10 feet, 10 feet. I might get some help with the calculations here, some really quick calculations here. 10 feet, 10 feet, 10 feet, and 10 feet. What I really did, all I really need right now is AX or AY and BY. So let's get AY and BY. So if I do a sum of moments about, actually, let's just right now get AY. If I do a sum of moments about B, what is that going to be? I'll have negative 30 times 30, 30 kips times 30 feet, plus AY times 40 feet equals 0. And so AY then is going to equal 30 times 3 over 4, right? 30 times 3 over 4. Oh, sorry about that. 30 times 3 over 4, it looks about right. And so then what is that? That is 50, huh?
22.5.
Thank you, 22.5. Which means that BY then, by simple sum of forces in the vertical direction, BY will equal 7.5 kips. So I know the force on the left and the force on the right. Unfortunately, I have way too many members in order to actually solve for this, to solve for the forces and all the members. So Let us look at how I would handle this depending on, I'm going to use the same problem to illustrate how I would handle this depending on whether the braces are slender or not slender. So, let us assume first, assume braces are slender. Now, what I'm going to do is, I'm going to use the method of sections and cut out, let's say, the left portion here. So this left portion, when I cut this, consider this for a moment. I have something like this here. And I didn't give all these joints names. Let's just go ahead and call this F1, F2, F3, and F4. And all of this is going to come together to do two things. Well, one, all this is going to come together to produce some sort of internal moment, and all of these forces are going to come together to produce some sort of internal shear. They're going to come together to produce some sort of internal shear. So I have my AY here, my 22.5 kips. My 22.5 kips. And then I'm going to have some sort of shear here as well. Some sort of shear force, a V and an M. Now, let's think about this here. Here is the question. Can F1 and F4 contribute at all to the shear?
No.
Why not?
It's in the horizontal direction.
Exactly, yes. That was a good quick answer, and yes, I was just seeing if you were just jumping to it, but yes. Or F1 and F4 cannot produce anything. I probably should show an arrow there. F1 and F4 can contribute nothing to the shear. The top chord and bottom chord contribute nothing to the shear. They're horizontal. Are horizontal, therefore contribute nothing to the shear. Nothing to panel shear. So let's think about this. They contribute nothing to the panel shear. So the only thing that will produce any kind of shear, and again, when I say panel shear, I am talking about the shear of the entire truss, treating the entire truss as a beam and just saying, okay, whatever forces are inside these members, I still believe in method of sections, and these must come together somehow to produce a moment like this and a shear like this. They have to. There's no other option. So ignoring the internal forces, if this force here, well, actually, I suppose that in this case, actually, this should be the opposite direction, shouldn't it? Sorry about that. That should be a downward arrow. Sorry about that. And that one would have to, in the moment, would then be counterclockwise to balance that. Sorry about that. So ignoring these internal forces and just saying these internal global forces are equivalent to these local forces, the shear here at this point has to equal basically a downward force of 22.5 kips. It must equal, although that would be positive shear and how we usually define shear, it would be a downward force on the right-hand side of the cut there, just like we saw with method of sections before. So let us discuss how we can produce that, though. So how can the web members, or the diagonals, produce that shear? Well, first of all, let's draw this out. So F2 and F3. We have F2, we have F3, as I drew it before, and we had 22.5 kips, and we said all of this, these two must equal a downward force of 22.5 kips. Now, as I have this drawn, they're not going to be both contributing to shear. And so, if I want them both to contribute to shear, what I would actually have to do, if both are to contribute to shear, to shear here, then I would have this kind of relationship here. If they're going to avoid canceling each other out, then I need both of them producing a downward component. So F2 would be like this, and F3 would be like this. Let me show you here. F2 would be in this direction, and F3 would be in this direction. And we'd have a 22.5 kip here. So basically the vertical components, or F2 would be in tension. Oh, it would be in...
When you're ready.
Okay, F2 would be in tension, and F3 in compression. And F3 in compression. So, however, though, if we are going to have a slender section, if sections are slender, then we cannot have any compression. No compression possible. Possible. So therefore, if F3 has to be in compression for this to happen, then F3 has to be 0, and F2 carries entire shear load. Carries the entire shear load, or in other words, the vertical component of F2 is going to equal 22.5 kips. Of F2 is going to equal 22.5 kips. And suddenly, based upon that, we have a known. We now have one more equation. Have one more known. And if we do that across each of the panels, that'll give us 4 knowns, and then we'll be able to have this truss be completely statically determinate. And so, so that is how we apply the first assumption, which is basically assuming that all of the shear is carried by a single diagonal in tension. And the opposite, we're going to split it between the two, but here we're going to look at, for this first assumption, we're going to consider only one of the members carrying all of the panel shear in tension. All right, and that is essentially our complete first assumptions case. So again, if our assumption is that our two diagonals here are both tension members only because they are slender, if they can carry only tensile load, we will assume that our compression member carries 0 load, and the tension member here carries a load such that its vertical component is completely equal to our panel shear. And that is one way we can produce one more known. And if we do that across one of each of our 4 panels, that will give us 4 knowns, and then we can turn the structure from an indeterminate one into a determinate one. So next I'd like to consider the second case, and that is if we have non-slender diagonal members. Our second case, non-slender panel members. So something that can withstand a decent amount of axial force, and we assume, or compressive axial force, in other words, so we assume that our panel or our diagonals can carry both compression and tension. Can carry both compression and tension. So for example, if we have the same truss again, same cut with the method of sections, like so, and we have the same 22.5 kips here, 22.5 kips with a shear downward equal to 22.5 kips, and then F1, F2, F3, and F4, F1, F2, F3, and F4. Well, in this case, I know they can't be both F3, or that's, sorry, F2. I know F2 and F3 can't be both in tension because their vertical components would then cancel each other out. So in this case, I would want both of them to go downward, just like previously. So let's say this is F2 is downward to the right and F3 is downward and to the left. So F2 then, just like we looked at last time, F2 is in tension and F3 is in compression. And in the previous case, when we said they were slender, we had to ignore the compression one and say, okay, well, this is in compression, this would be in compression, that's the only way it can carry any kind of shear load, but since we're assuming these members can't carry any substantial compression load, we're going to assume that F2 carries the entire panel shear and tension. However, if we can get compressive load out of this, we can go ahead and assume that they both carry an equal share of the shear. Both carry 1/2 of the panel shear. So we'll go ahead and assume that they both carry 1/2 of the panel shear. So in other words, assuming they have the same slopes, F2 is generally going to be equal to F3. And so basically, and what would that equal though? F2 would have to be equal to, and that force that they equal would be equal to 1/2, or their vertical component of F2, the vertical components of F2 and F3. F3 will be equal to 1/2 of the total shear. Maybe it would be good to work through a numerical example of total panel shear. So let's try working through a numerical example. So let's say I have, let's make this a fairly simple truss. And let's just go ahead and provide some numbers on this. So normally if we just have one brace, not just a single diagonal brace, not this X brace, we still have a truss that's nice and statically determinate. With this, because we have the 2 extra braces, this is going to be indeterminate to the 2nd degree. So if I were to then give some joint names, let's say A, B, C, D, E, and F. And then let's give some dimensions. Let's say from D to E, I don't know, let's say this is, let's say D to E is, 8 feet and 8 feet, and then let's make it 6 feet high. So kind of a very short bridge here, and 6 feet like so. Then let us also say that there is a load applied at B equal to, 20 kips. Let's apply a 20 kip load downward at B. So that in turn means that I would have reaction forces of 10 and 10. 10 kips and 10 kips at both F and E, or F and D. So let me then go and isolate this. Let me isolate use method of sections here. And let's look at what kind of forces are here. And maybe I'll go ahead and calculate the actual member forces, the actual FAE and FBD, depending on whether they're slender or non-slender. Our diagonals are slender and non-slender. So we have essentially this here. If we have A, D, and then let's see, let's draw some forces. Maybe I'll make this a little bit bigger. D, and then FAB, and let's say FDE, and then let's say FDB and FAE. In terms of slopes, let's go ahead and put some slopes on there. I know this is going to be a 3, 4, 5 triangle, so like 4, 3, and 5, and the same here. 4, 3, and 5. Now, looking at the shear here, if there's an upward arrow here, there must be a downward shear arrow here, and that is going to have to be equal to 10 kips. So I'm going, if I cut this out, if there is a 10 kip force here to the up, or to the upward, there has to be a 10 kip force downward here. And so then, now in turn, in order for these not to cancel each other out, if they're going to be equal, I need to make FDB a compressive force rather than a tensile force. And so then looking at the, working through the equilibrium, well, let's first work through two different options, or the two different assumptions. Assumption case 1, maybe let's call this case 1. Slender diagonals. In that case, FDB has to be equal to 0. FDB has to equal, or BD. Well, I guess I used DB here, so let's keep using that. FDB equals 0 because no compressive force possible. Like if these were just like ropes or something like that, no compressive loads can be carried. So if we have no compressive capacity, so therefore FAE times 3 over 5 is equal to 10 kips. The vertical component of FAE must be carrying the entire shear load for this panel. And so then FAE is equal to 10 times 5 over 3, so 50 over 3. 50 over 3 kips, whatever that comes to. 50 over 3 kips there. So we have that. Does that make sense? 50 over 3, yes, that sounds about right. That would be the vertical component of that. And then case 2, so we would have FAE and FDB. We know the force in both the diagonals. And once we know that, we could do the same thing on the other panel, and that would now make this truss statically determinate. Case 2, non-slender diagonals. I'm going to assume that both FDB or DB and AE can carry load. So in other words, one will be in compression, but one will be in tension. That will be fine because we have reversible numbers. We're using something like a W section, not something like a simple steel cable or something like that. So let's see. Let's look at this. Now the vertical components here. I basically want the vertical component of each to add up to 10K. So FDB times 3 over 5 plus FAE times 3 over 5 will be equal to 10. However, I also said that I'm also assuming that they're going to carry equal load, so I can really just say 2 FBD times 3/5 equals 10, or FBD, well, let's see, that's going to equal 5 times 5 over 3, or simply 25 over 3 kips. 25 over 3 kips, and that's equal to both FBD and FAE. So both of our members carry the same load. So basically, here FAE, the force in member FAE equals 10 kips in tension, and the force in member FBD would equal 10 kips, or not 10 kips, 25 over 3 kips. 25 over 3 kips in tension, and FBD would be 25 over 3 kips in compression. They're going to be carrying equal and opposite loadings such that they both add up to half, or they both contribute to half to the total panel shear. Now, in reality, this isn't going to be exactly true. These members will probably carry similar similar shear loads, but they won't each exactly carry half of it. But again, we are referring to these as approximate methods, or refer to these as approximate methods. They're not 100% accurate, but they do allow you to get loads without relying on the elasticity or the stiffness of the members. So even without knowing anything about what these members are, as long as I just assume they're slender or non-slender, I can come up with loads that will allow me to do an initial member sizing, which I can then use for further iterations using more precise stiffness methods or computer-based methods. All right, that'll do it for part 1 of this video, or part 1 of this lecture. I also want to do some parts 2 and possibly part 3 covering approximate methods for other types of structures. That'll do it. Thank you for watching. Hope you all enjoyed this. Hope you all learned anything, learned a few things. Let me know if you have any questions, and as always, thank you.